Okay. So as I said, this is the last week. I will try to go as far as I can today. And if there is anything left, we will complete it on Wednesday. You have graded problem for chapter 5. When is it due? Anybody remember? I can check that. Graded problem? No. Oh, it's last year then. I have to change the date. I will make it Wednesday. The graded homework problems. Then on Wednesday, I'm going to give you the take-home problem, which will be due on exam day. I think I should give it to you on Wednesday so that if you have questions about it, we will discuss it on Friday. I think it's 3. Just 3:10 to 5:10. A game takes more than 2 hours, so you will still meet the game. That is what happened to football. Soccer, you plan 2 hours. Hardly will it extend more than 2 hours. So I'm going to fix that. And then I will post chapter 6 homework. I don't generally graded problem for chapter 6, but any problem that will be on the exam on chapter 6, you will see it on the take-home problem. You will see chapter 6 on the take-home problems. We have finished section 1, we are going to do section 2 and maybe begin section 3 and end section 3 on Wednesday. That's what I usually get to. So last week we learned about the uniform distribution as an example of continuous random variable. So another type of continuous random variable, 6.2, the exponential distribution. We know the exponential function. I want to show you an integral here, which is going to be useful in exponential distribution. Integrating. Oh. So if we have a function f of x equal to e bx, what will be the integral of e bx from negative infinity to infinity, for example. Integrating negative infinity to infinity e bx dx. So this integral is equals to integral from negative infinity to 0 e bx dx plus integral from 0 to infinity e bx dx. So let's just work this one. EBX dx, improper integral. So equals to 1 over b e bx plus c. Essentially what I want you to remember. So look at this one now. Negative infinity to 0, EBX dx is equal to the limit as x tend to, let me use t, not x, as t tend to negative infinity of EBX 0 to t. Which is equal to limit of EB t at t tend to negative infinity. I'm sorry, I did not write it properly. Here is 0 and here is negative infinity. Do you see why? It's from negative infinity to 0. For that reason, we are going to apply 0 first. E of 0 is 1 minus limit of EBX. Sorry. I replace by 0 and then I replace by t. Look at what I'm doing. The antiderivative is here. At the place of negative infinity, I put t and make t go to negative infinity. This is just notation for us to understand how to do that. So as t tend to negative infinity. What is this limit? Can you think about for 1 minute? What is this limit? Yes. Will it be 0? What about b? Think about b. What will you do with b? Suppose b is minus 1. Yeah, so that is if it was e to the minus t, as t tend to minus infinity, what will it be? So what did you say first? Let's go with what you say. It will be 0. If b is negative, will it be 0? It will be what? Infinity. When it is infinity, the integral does not exist. That's what we say, but some people still work with that kind of situation. Do we understand what I'm saying? The integral is not convergent if it goes to infinity. And it will go to infinity if b is negative. This is the important part of what I want us to see. And if b is positive, this will be 1. So the same thing is going to happen on the other side from 0 to infinity. If b is negative, it will be 0. If b is positive, it will be infinity. Do we see what I'm saying here? Is the reverse. So now we want to use this to define the exponential distribution. Let x be equals to the interval from 0 to infinity. Find b so that Now find k. I want to say call this k. Find k so that f of x equals to e to the minus bx, if b positive, is a density on x. Find k so that f of x equals to k e to the minus bx is the density on x. Then we will have that f is a density if the integral from 0 to infinity f of x dx is equals to 1. That is integral from 0 to infinity k e to the minus bx dx is equals to 1. And this integral will be k over b e to the minus bx from 0 to infinity, which is limit as t tend to infinity of e to the minus bt k over b here. Minus 1. Nope, not minus 1. Put a minus here. Equals to 1. And this limit equals to what? If b is positive, this will be equal to this. What will this be if b is positive? B is positive, there is a negative here. Thinking of what we said before. E to the minus infinity. What is e to the minus infinity? 0. So this is equal to, with this minus 1, k over b equals to 1. So k equals to b. So this distribution is called the exponential distribution. We are going to define it as equal to 0, infinity, as an exponential distribution if its density function is of the form f of x equals to lambda e to the minus lambda x for x greater than or equal to 0 and 0 otherwise. It is connected to the Poisson distribution with mean lambda. Actually, Y is a Poisson distribution. With mean lambda. Then the time until the next incident is an exponential distribution. So we are saying that if lambda is the number of incidents that will occur in a given period of time, the time until the next incident is an exponential distribution with density function f of x equals to lambda e to the minus lambda x. For example, if we say that a patient that has a flu will sneeze in average once every hour, then that is a Poisson distribution. The number of times that person is going to sneeze within an hour is a Poisson random variable. So if you meet that person, the time it will take before that person sneezes is a continuous random variable, which is an exponential random variable. If the person sneezes once, the time until this person sneezes again is an exponential random variable. So we are going to, together we will compute the moment generating function of an exponential distribution, the mean, the variance, and the standard deviation. So I can tell you that the mean is 1 over lambda, the variance is 1 over lambda square, and the standard deviation is 1 over lambda. Remember that for Poisson, the mean and the variance were the same. For exponential distribution, the mean and the standard deviation are the same, and it is 1 over lambda. So I want us to work through this together. First, we will find the moment generating function. And if we get the moment generating function, we will use the logarithm of the moment generating function for the formula that we learned in chapter 5 that can help us to determine the first, the mean and the variance. We can also compute it directly, but it will take a longer time. So let me start with moment generating function. We have had a lot of examples already. When I was giving you example, I had the exponential distribution. When I say f of x equals to 3 exponential minus 3x, I know that it is a density function. Okay? So to save time, we will do more example on Wednesday and Friday. Moment generating function. Of an exponential distribution. X, let's say x 1 over lambda. So we call it x1 over lambda because the mean is 1 over lambda. And we will recall that this lambda is actually the mean of the Poisson distribution associated with the exponential distribution. So the mean of x is the integral from 0 to infinity of x, f of x dx. Oh, I meant to use the moment generating function. Okay, let me do the mean since we are on it. So, which is and the moment of x is the mean of etx, which is the integral from 0 to infinity etx f of x dx. And it is from 0 to infinity. Etx lambda e to the minus lambda x dx. And this is lambda integral from 0 to infinity. Etx e to the minus lambda x dx. You are, if you like integrals, you should be enjoying this part. And this is lambda integral from 0 to infinity e to the minus lambda minus t x dx. Which is equal to lambda over lambda minus t e to the minus lambda minus t. So this minus is because of the lambda, the minus which is here. This minus is because of the minus which is here. So now, to do this integral will be finite only when lambda minus t is positive. So we will say if lambda minus t is positive, then mx of t, if lambda minus t is positive, then this will go to 0 at infinity. And to 1 at 0. So we will do 1 minus minus, and it will be lambda over lambda minus t. So moment generating function of x is lambda over lambda, where t is less than lambda. You see why t is less than lambda? Because we want this number to be positive. Lambda is greater than t. So h of t equal to the logarithm of mx of t will be the logarithm of lambda over lambda minus t, which is lambda. You can put a minus here, logarithm of lambda minus t. H prime of t, h prime of t is minus lambda. The derivative of lambda minus t with respect to t is 1. Over lambda minus t.
There is something missing here. Here. Mm-hmm. Mm-hmm. Let me take this one. Now, this is where the problem is. I'm sorry for this. So we could leave it this way. Leave it this way. Or write this as, it doesn't hurt when we do this. You see what I'm saying? Logarithm separate. Either you separate it this way. And now, what is h prime of t again? In this case, h prime of t is going to be 1 over lambda minus t. Because lambda is a constant, so this part is going to go to 0. The derivative of lambda, logarithm of lambda will be 0. And this derivative will be minus 1 over lambda minus t. Because of this minus, it will become 1 over lambda minus t. And h prime of 0 is equal to 1 over lambda. Is E of x. Now, what is the second derivative of t? Second derivative, 1 over lambda minus t squared. The variable here is t. So the second derivative of 0 is 1 over lambda squared, which is the variance of x. So E of x equal to 1 over lambda. Variance of x, 1 over lambda squared. Standard deviation, 1 over lambda. So if beta is equal to 1 over lambda, then we can define f of x as 1 over beta E of minus E of minus x over beta. So this is another definition of the exponential distribution. And in this case, we will say that the mean is beta, the variance is beta squared, and the standard deviation is 1 over beta. And then the moment generating function, we can write it again as it was lambda over lambda minus t, right? We can write this as 1 over lambda times 1 over 1 minus t over lambda, which is 1 over 1 minus t over lambda, which is 1 over 1 minus beta t. It's just a way to express it in another way. I want us to prove something that we saw on the geometric distribution here. Geometric distribution was in chapter 4. It was the memoryless property of a geometric distribution. I want us to connect this to the geometric distribution that we have learned before. It has the same property as, there is a property here that I want us to prove for, I think it was from your textbook. Anyway, it wasn't in the note, it was a homework problem. Example. At x equals to 0, an exponential random variable with mean 2. And the probability that x is less than 1. Suppose you have a question like this. Let x be an exponential random variable with mean 2. Find the probability that x is less than 1. Then we will say that if e of x equals to 2, then lambda equals to 1 over 2. This is what we, and the density function f of x equals to 1 over 2 exponential minus x over 2. And the probability that x is less than 1 is equal to integral from 0 to 1 f of x dx, which is the integral from 0 to 1, 1 over 2 minus x over 2 dx. And what is this equal to? What is the integral of half exponential minus x over 2? Should it be negative 1 over 4? What is the derivative of x over 2? What is the derivative of exponential minus x over 2? Yeah, because if you wanted to do the antiderivative, you will divide. You will divide, right? And now you will divide and multiply by what you have. So this will be which is, there is a minus here because of this minus, which is 1 minus e to the minus half. Does it make sense? Now let's find the cumulative distribution. X be an exponential distribution. You know it's non-negative distribution with mean 1 over lambda. Sometimes we will say mean beta, mean 1 over lambda. And the cumulative distribution of x is f of x equals to the integral from 0 to x over t dt. Which is equal to the integral from 0 to x. F of t is lambda e to the minus lambda t dt, which is minus e to the minus lambda t 0 to x, which is equal to minus e to the minus lambda x, 1, which is 1 minus e to the minus lambda x. So the cumulative distribution the cumulative distribution function of x is f of x equals to 0, x is less than 0, 1 minus e to the minus lambda x, is 0 is less than or equal to x, as the cumulative distribution of x. We do another example. At a busy intersection, it is known that on average, there are 2 accidents per week. If there is already 1 accident, no, let me not put it this way. What is the probability that the first accident will occur in within, let's say, 1 hour. So we are saying what is the probability that the time it will take for an accident to occur will be less than 1 hour. Will be less than 1. So T is an exponential distribution. With mean 1/2. T is an exponential distribution with mean 1/2. So P of T less than or equal to 1 is equal to f of 1, which is 1 minus e to the minus 1/2. So I wanted you to see how problems connect Poisson distribution to exponential distribution. So in exponential distribution, we are counting the number of incidents that will occur. In Poisson distribution, we are estimating the time it will take for an incident to occur. Okay. Will you continue? So I gave you the same problem, but presented in a different way. So I'm going to specify it on, we will submit the graded problem for chapter 5. It's part of the problem that I gave you already. I gave you all the problems for chapter 5. I'll select some to grade, and I will send you, I think it should already be on Canvas. I will send it to you, and let's say we will submit it on Wednesday.